Hi, I'm Justin Chalker, a lecturer in synthetic chemistry at Flinders University in Adelaide, Australia, and it's our pleasure to share with you some of our recent research in using allyl sulfides in olefin metathesis. This research is featured in two recent publications. The first is a review article in the Australian Journal of Chemistry that explores how allyl sulfides have been increasingly used in olefin metathesis, especially in synthesis and biochemistry. The second paper is in Chemical Communications, and it features our work in using allyl sulfides as traceless promoters in challenging olefin metathesis reactions. Allyl sulfides are remarkably reactive in both ring closing and cross metathesis. This reactivity has enabled this reaction to be carried out in open air or even in water. The high reactivity of allyl sulfides in metathesis was surprising given the many examples where sulfur was detrimental to olefin metathesis, and one example is shown here. Alois Fürstner found that there was a quite general incompatibility of sulfides with ruthenium metathesis catalysts. Allyl sulfides, it turns out, are the exception to this rule. The sulfur in allyl sulfides isn't merely tolerated by ruthenium metathesis catalysts. The sulfur actually enhances the reactivity, and it does this by binding to ruthenium and bringing the alkene of the allyl sulfide into close proximity to the alkylidene, provoking subsequent metathesis events. If the alkene is extended by 1 or 2 methylene units from the sulfur, no metathesis occurs. The catalyst is sequestered as a stable chelate. When an allyl sulfide is the substrate, this sequestration is not observed. There's no stable chelate that can form. Since our discovery that allyl sulfides are remarkably reactive in olefin metathesis, other labs around the world have incorporated allyl sulfides explicitly into their substrates in order to promote olefin metathesis. This has enabled access to covalently modified proteins, therapeutic peptides, dynamic combinatorial libraries, and a variety of building blocks for organic synthesis. Given the increasing use of allyl sulfides in olefin metathesis, we sought to clarify which catalysts are most suitable for this transformation. And what we discovered was that ruthenium catalysts that are phosphine-free and contain an N-heterocyclic carbene ligand are the most appropriate. A phosphine-free catalyst is critical so there's no ligand that competes with sulfur in its binding to ruthenium. Sulfur binding to ruthenium is a critical step in allyl sulfide-promoted olefin metathesis. A second key finding in this research was the demonstration that allyl sulfides can be used to promote metathesis reactions en route to products that don't contain sulfur. This was accomplished by building substrates that contain an allyl sulfide that initiate metathesis but are cleaved from the substrate en route to the final product. It's also worth noting that these substrates are remarkably easy to build in a connective fashion, and that's due to the versatile chemistry of sulfur. The key findings in this research are summarized below. First, allyl sulfides are remarkably reactive in olefin metathesis, provided they're paired with a catalyst that's both phosphine-free and contains an N-heterocyclic carbene ligand. Secondly, allyl sulfides can be used as promoters to access targets that don't contain sulfur. In this way, we use the allyl sulfide as a traceless promoter for challenging metathesis reactions. This research was led by a talented master's student in my lab, Grant Edwards. Grant is currently pursuing his PhD at North Carolina State University in the Pierce Lab. We also thank Philip Kolb, an undergraduate in my laboratory, for his key contributions to this project. Finally, I'd like to thank my collaborators and mentors over the years who have inspired much of the research that we've talked about today. I encourage you to read through the story behind the paper to see how these collaborations have informed this research. Finally, I'd like to thank you for your time and attention, and I hope you enjoyed our first contribution to external diffusion.